All right, this is 7.1, Rational Graph Properties, Day 2. So if it's been a while since you took the quiz or looked at 7.1, Day 1, I highly suggest you pause this, just go back, look over your notes. We will review it at the end, but I think you'll have a little bit better understanding of this if you just go through those, look through them, just kind of remember what the heck is going on. I also want to give you a visual before we begin the notes, so let me go into, oops, wrong thing. I gotta remember where it was at. Here it was. No, it wasn't. There it is. All right, back to business. So, if you remember the last lesson, we talked about how we're working with rational functions. So we're working with fractions that have x's and we're graphing them, all this stuff that we talked about, right? All right, so we have y equals, and this is the example I gave earlier. So this basketball player, green means that he made them or she, and then red x's means that they missed. So I counted them all up, and there was 3 out of 16. So if this basketball player just wanted to see what their shooting percentage could be right now, real quick, let me look at it. 3 divided by 16 is only at 19%. So, I mean, 19% shooting, that's not that great, right? So if they want to see, all right, I'm already starting at 19%. By the end of the season, how good could I get? How good could my percentage get? So let's say that this player never misses again, which is very unlikely, but just hoping for the best, right? Well, what could I get? So if we graph that on our calculator, and only look at makes, right? So they shoot another, they make another. So then it'll be 4 out of 17, right? So for when we plug in 0, we're already at 3 out of 16, or so this will be 100%, and then this is the 19% where that dot is, right? So as this person continues to shoot and make more and never miss, just hypothetically, like, what could they reach if they just kept doing this? They'll continue to grow, right? And then it'll slowly, I mean, this is not to scale, but the more they make, the closer and closer they'll get to 100%. But they can never actually get to 100%. And this is called an asymptote. This is actually a horizontal asymptote. So it's an imaginary line that the graph is going to try to approach, right? It's going to get closer and closer to 100%, but this person will always be 13 off. So even if he makes the next 1 million, right? 1 million, let's just do 1,000. He makes the next 1,000 shots. He's still 1,000, oh my goodness, sorry. He's still 1,003 out of 1,016. Now that's a very high percentage, so 1,003 divided by 1,016, if this person was to make a lot, that's at 98.7%. But this person can, no matter if they just make and never miss again, they can never get to 100%. So here's an example of an asymptote. Here's another example. So if in your calculator you type in y equals 1 over x, you're going to see a graph like this. And it's very interesting that it's making this shape, like just this simple fraction. But if you kind of think about it, anything below 1, that input will be like 1/10, right? 1/11th, whatever, right? So as I'm looking at these small fractions, but as I put those in, when we divide by a fraction, we're actually multiplying by the reciprocal. So when we plug in a really small number in for x, we get a big number as the output, right? So if we plug in 1/10, our output's 10, okay? And so we can get a really, really, really small number, 1 over 999, right? And then, so if we get 1 over 999, we're at 999. We're really tall. But we'll never actually get to 0, right? No matter how small of a number we plug in, the smaller the number plug in, the bigger the output will be because of that dividing by a fraction, right? But we'll never actually reach 0. So here we have another asymptote. It's just an imaginary line that the graph will never actually get to. It'll get really close, but never actually gets to. we can see we have another one here because y will also never become 0. So x will never become 0, y will never become 0, because if x becomes 0, then there's no answer because you cannot divide by 0. So we have some asymptotes here that are these imaginary gaps, right? I mean, it's a real gap, but it's an imaginary line that the graph just can't touch because of how the math's working. And if you have any more questions on that after this, please let me know. All right, so an asymptote. We're going to talk about that in this next box. We're going to learn and apply steps to finding vertical asymptotes, learn and apply steps to finding horizontal asymptotes, and then review everything we learned before. So like I said, we will review. Okay, so here we go. I can find the vertical and horizontal asymptotes. I can see how they relate to the other key features. So an asymptote is an imaginary line, so let's kind of change that, is an imaginary line. You're not going to see it on your calculator, but it is a line, so we could have just said it's a line that a graph approaches as it heads toward infinity. And it can head towards negative infinity, but there are several different kinds of asymptotes. We'll be working with two types, the vertical and horizontal. We won't be working with the oblique today. A graph of a rational function can have many, so it can have any number of vertical asymptotes. So be prepared for lots of vertical asymptotes, but no more than one horizontal asymptote. Additionally, horizontal asymptotes can be crossed. You can cross horizontal ones, so crossed, but a vertical asymptote will never be crossed. I still remember when I took junior math a long time ago, my teacher, I had this older teacher, Mrs. Nilsson, and she always said, red hot asymptotes, because you're not supposed to touch it, right? The graph will never touch it. So she said it's like an oven. The vertical asymptotes are like a red hot stove. So red hot asymptotes. We'll never forget that. So, all right, horizontal asymptote. You can touch and you can cross, but not very often. So we'll look at that next. Today we're just exploring them, but not in graphs. We're not going to do obliques. That's an honors topic. So if you're headed towards honors, maybe come see me before after school. We can chat about them, but we're not doing them in this course. Okay, so that's what we're looking at. So the how-to right here, what do I do? How do I find these lines that are directing the graph, right? Directing that fraction. How do I find them? Well, here you go. Well, asymptotes can downgrade to become wholes. And so whenever we cancel out, when we factor and then are simplifying our fraction, if we cancel anything out, we're going to get a whole. Wholes are still points of discontinuity. They're still breaking up that line, but they're not this line, that guides the graph. It's not an asymptote, it's kind of a downgrade. So it'll still break up the continuous flow of the graph, but like I said, a downgrade. All right, so if you are looking for asymptotes, you're going to factor. So step A says factor. Both the numerator and the denominator, see if you have any factors in common that can be canceled out. So for example, I factor, I get x plus 2, x plus 1, and in the denominator I factor, and I get x plus 2, x minus 3. Okay, so I factored both the numerator and the denominator, and then I notice x plus 2 can be canceled out. And so that means I have a whole, and you set it equal to 0, we'll see in the notes. I have a whole at -2. All right. The graphing calculators, if you try to put this in your calculator, you will not, you won't see the hole in the graph. But the table will show an error, and I'll show you how to do that either this time or next lesson, maybe next lesson. Okay. So after you see if anything will cancel out, if you're still left with stuff that doesn't cancel out, you're going to have a vertical asymptote. Vertical asymptotes are located in the denominator, so it's still in line with points of discontinuity. Vertical asymptotes are, like I said, going to be found in the denominator. So these are vertical lines written as x equals. So you're going to take your denominator, set it equal to 0, add 2, add 2. So x equals 2 is our horizontal asymptote. So when we graph it, we're going to go to x equals 2, and we're going to have this imaginary line that the graph won't be able to touch. All right, so in this other example, 2x minus 3 equals 0, we solve for x. So we add 3 divided by 2, we get x equals 3 halves. All right. So once a rational function is simplified, vertical asymptotes may be found by setting the uncanceled denominator factors equal to 0 and solving for x, which I just showed you. So that's how you'll do those. Okay, horizontal asymptotes are a little bit different. So horizontal asymptotes are kind of like that basketball problem that I told you, where just because of the nature of the numbers involved, we can never get to a certain value. So it kind of limits us horizontally or limits us underneath. So like the basketball problem, if you remember, at 100% we could never get there. So there was an asymptote just kind of guiding this line, saying you're going to get really close as you make more and more and more shots, but you'll never get to 100%. You blew it in your first game. Okay, so horizontal asymptotes, they can be crossed. Vertical cannot. Red hot. Just remember that. Okay, so to find a horizontal asymptote of a graph of a rational function, compare the degree. So think of the alphabet. M comes before N. So here, in this first example, why are you not writing? M equals 2. N equals 2. So we're going to look at the degree. So it says to find a horizontal asymptote, look at the degree. M is in the top, N is in the bottom. So think of the alphabet. M comes before N, M in the top, N in the bottom. So M in the numerator, N in the denominator. So DN, dungeon, maybe. I don't know, something to help you remember, right? Okay, and then we kind of have this guide here. If M equals N, which is happening in this example, then you're going to take your leading coefficients. My leading coefficient is 1 and 3. So 1/3, 1 over 3 is my leading coefficient. Horizontal is going to go horizontally, so it'll cross through the y-axis. So we're going to have y equals 1/3 as our horizontal asymptote. Now let me explain why. Like, people didn't just say, all right, if M equals N, let's say that this is what, no, they didn't just make it up, okay? So what's actually happening is as we plug in lots and like big numbers for x, the bigger the number is we plug for x, think about it. If you have like 999 squared, that's going to be huge, right? So as we get really big numbers in these two x's and square them, they're both going to be really big. So since they're so big, anything being added or subtracted doesn't really have that much of an impact on the problem. But this multiplier has a bigger impact than adding and subtracting, right? So you can kind of think about it like that, is that minus is just going to be kind of insignificant as these numbers get huge. But if you have a big number multiplied by 3 compared to 1, that will influence the problem a lot. So that's why we have a horizontal asymptote at 1/3 when our degrees are the same. Because when your degrees are the same on those big numbers at the beginning, right? So as we plug in big numbers for x or really small numbers for x, they're basically controlling that problem because squaring it is just going to make it either really much bigger or really much smaller. And so they are kind of equal in the top and the bottom. So the only thing that's really affecting it is that multiplication to those of 1/3. All right, so then if our m is less than n, which is happening here, because remember our m is 1, our n is 2, we're just looking at the degree. M is 1, n is 2. m is smaller, right? So if m is less than n, the graph has a horizontal asymptote at y equals 0. And this is, like, if you kind of think about it, as we start to plug in really big numbers for x, right? Really, really huge numbers, right? So if you have $1 million, does one extra dollar really make a difference in, like, your big money, right? If I already have $1 million, $1 is like, yeah, give me the dollar, I don't care. Like, it's not gonna make that big of a difference, right? So subtracting $1 or adding $2 in big, big numbers or really, really, really small numbers isn't gonna make that much difference to that x, right? Okay? And squaring in the bottom will always keep the big, big denominator, right? So it's gonna get close, like this is gonna become, so like 1 million on the top, 1 million squared on the bottom's gonna get so much bigger that it just gets, as we get bigger numbers, it keeps getting a smaller, smaller, smaller fraction, getting us closer and closer to 0. Okay, and the same holds true kind of with m is greater than n. There's no horizontal asymptote because the numerator is going to get so much bigger than the bottom so it's like we have 1 million in the top and a little bit in the bottom. The top's so big that, I mean, we just get kind of a normal number when we're done. Okay, all right. Sorry. It's being really slow, not really responding. Okay, so here we go. We're going to talk about putting this all together. All right, so you get a problem, and it says, what are your holes? Well, remember you're going to have to factor first, and if anything cancels out, it's your hole. So nothing cancels out, so we don't have any holes in our graph. We do have a vertical asymptote. Remember, vertical asymptotes always come from the denominator because x cannot be -5, right? So if we set that equal to 0, find our point of discontinuity, -5 will cause problems because we'll have 0 in the denominator, if you remember from last unit. So x equals -5 is our vertical asymptote. Now our horizontal asymptote, we're going to look at our m, which is 1, and our n, which is 1 in the denominator. They're the exact same. So we're going to have a y horizontal asymptote at our coefficients, and our leading coefficients are 1. So we have a y equals 1. We're going to basically cap this problem out at 1. Okay, that fraction, it's going to go to 1. That's where it's headed, okay? Okay, all right, so B, let me explain that real quick. Hopefully this helps you understand the horizontal asymptotes. Okay, so I'm just going to use it in terms of money. So if I had tons and tons of dollars, right? Let's say I was a billionaire. Okay, so if I had 1 billion minus 3 divided by 1 billion plus 5, when we divide those, what we plug in for x, billion minus 3, billion plus 5, minus 3 plus 5, when you're a billionaire, are you going to care if somebody steals $3 from your wallet, right? You have $1 billion and somebody just took 3. That's like someone taking pennies from you right now, right? I mean, you might be a little bit bugged, but really it's not going to change your financial future, okay? So, billion minus 3, billion minus 5, I mean, it's still lots of money divided by lots of money, which basically eventually is going to head towards 1, right? Kind of like the basketball problem, okay? He was 3 out of 16, okay? The more he made, the closer he's going to get to 100%, but he can never actually reach 100%, which we're going to call 1, right? So you get closer and closer and closer to 1, but you're not going to ever get there because you are a little bit off, okay? But you're going to get really close. So that's why there's a horizontal asymptote at 1. This fraction's going to start to get towards 1, but we'll never get there, okay? All right, holes. So first step, factor. So if you have any questions on factoring, please reach out to me. You should be pretty proficient at factoring and know how I'm getting those numbers. But if not, let me know. Okay, nothing cancels out. So there are no holes. We have a vertical asymptote at -3 and -2. I just set both of those equal to 0. Points of discontinuity are my vertical asymptotes, okay? Because this graph can never go to where x is 0, okay? So, and it'll become, or sorry, where the answer is 0, and it'll become 0 at -3 and -2. So we have a vertical asymptote. The graph just won't appear there. Okay, now looking at our horizontal asymptote. We're going to look at our m and at our n. Now you can memorize that up there, but our m is 1 and our n is 2, looking at that, right? Okay, so if we have infinity in here and infinity in here, right? Infinity squared is going to be so big, right? So big that when we try to divide the top divided by the bottom's still so much bigger that this is going to try to get towards 0. The fraction's trying really hard to get 0, never actually get there because of the other stuff, but it's going to try real hard. So horizontal asymptote at y equals 0. Okay, a few more examples. If you're kind of tapped out, go try the assignment, come back for the other examples if you get stuck. But I'm going to keep on going on. Okay, so factoring. Okay, something canceled out, right, as I factored. And so that's my whole. And don't forget, we have to set that equal to 0 to actually find out where the whole is. So the whole's at -1. Now the vertical asymptote is any uncanceled, non-canceled out factor. So we have one at 1, and then we're going to look, oh yeah, our m is 1, our n is 2. The bottom's so much, it's going to get so big compared to the top that we're going to try to get to 0, but we'll never actually get there because we're going to just create this smaller and smaller fraction, right, as we plug in bigger and bigger numbers for x, but we'll never get there. Okay, all right, and D, quick factoring. I'm going to get x squared plus 2x minus 3, which is x times x plus 3, x minus 1, all over x plus 3, x plus 1. Okay, all right, wholes. Any canceled out factor is a point of discontinuity still, but downgrades to a whole instead of an asymptote. Vertical asymptote we have at -1. Horizontal asymptote, okay, the top is cubed. M is cubed. N is squared. M's going to get so big, it's going to get big faster than the bottom, right? And so the bottom won't be able to catch up. The top will always be bigger. This stuff will make influence, but not so much. And so the top will be so much bigger that, I mean, it's just going to become a number, like 1 billion divided by lesser billion, right? And so the top is bigger, so it's kind of like 5 divided by 2. We're just going to have numbers that keep growing. The top's going to grow a little bit faster, but it's just going to keep going. So there is no horizontal asymptote. All right, so before we do example 3, which is kind of a recap of everything that we've learned in 7.1, you might want to make flashcards for this unit. I'm going to post something on Canvas that I think is a good idea, just an option, but like there's a lot of things that you got to remember, so might be a good idea to make some flashcards. Okay, and like I said, if you're like, okay, I got this, and you don't want to do this review, this video kind of got long, so you can tap out anytime. All right, I'm going to factor this real quick, though. Okay, so we have x minus 4 all over -3 times x minus 4 times x plus 2, which means we have a point of discontinuity at 4 and -2. The one at 4 is removable. It can cancel out, meaning that originally it can still be there, or we can cancel it out and we'll still have the same problem, right? We get the same answers there or not, because it's like a reduced fraction, right? Okay, but -2 is non-removable. It has to stay in the simplified version or we'll have a different problem. Excuse me. Okay, x-intercepts. If you remember, your x-intercepts are going to be involving the x's, but the denominator x's found the points of discontinuity, so it is the numerator x's that help us find the x-intercepts. And x-intercepts always hit the x-axis, which means our y value is 0 there. All right, so then we're just going to solve for x, and we're going to get 4. Okay, our y-intercept is when x is 0, right? So we hit the y-axis when x is 0. So I'm going to go back to the original function and just replace all the x's with 0. In x-intercepts, notice we replaced the y with 0. Here we're going to replace the x's with 0. Now you can kind of do this one in your head. You don't have to write it out like I always do. But 0 minus 4 is negative 4. 0 plus 24 is 24. So we get negative 1/6. So 0 and negative 1/6 is the answer there. Perfect. Okay, so our domain actually has lots to do with our points of discontinuity. If you remember back in like 9th grade and grades earlier, most of our domains do, all the x's are used in the graph, right? Our graph goes left and right forever. So domains are usually negative infinity to infinity. But we have discontinuity, right? We're not continuous. And so we have to look at our points of discontinuity, and they will disrupt this graph. And so I just kind of say, all right, negative infinity up to negative 2, we're going to have solid continuous graph, domain. But we got to hop over negative 2. Negative 2 up to 4, we're good, going to have graph. Then we've got to hop over 4, and then 4 to infinity, we'll also see some graph. Okay, we did have stuff cancel out. So that means we have a hole. So our removable ones are our holes, right? And then we have a vertical asymptote at our non-removable. And then we've got to go up, analyze. Okay, so our m is 1, and our n is 2. So our n, is bigger. So if the denominator is bigger, this thing's going to try to get to 0. It'll never actually get there, but it's going to try real hard to get to 0. The fractions will just keep getting smaller and smaller and smaller fractions because our denominator is bigger, and so y equals 0. Okay, point of discontinuity for f. We got a factor. If you hate factoring, you've really hated this quarter, right? Okay, 4 times x squared. Okay, so continue factoring. Hopefully you're doing this, not just watching their board, right? Okay, factored out, cancel out. Okay, we have point of discontinuity at 3 and negative 2, so I'm looking at the denominator. Types. We got a removable guy, removable, and we have a non-removable. X-intercepts, we're going to look and see if we have any factors that didn't cancel out. So we have y equals, what am I writing? So we do have 2 factors that didn't cancel out, the x and the x plus 1. So when we want an x-intercept, our y becomes 0. And so we have an x-intercept at 0, 0, and one at negative 1, 0, as we solve for x there. Okay, our y-intercept, I'm going to replace everything with 0. So when I'm just going to look up at the top. I'm going to have my y-intercept is 0 cubed, which is 0, minus 2 times 0 squared, which is 0, minus 3 times 0, which is 0. So I have 0 minus 0 minus 0, which is 0. 0 divided by anything. I don't even need to do the bottom, because 0 divided by anything, whatever I get on the bottom, who cares, is 0. So my y-intercept's at 0. Domain. Continuous domain would just go left and right forever, because domain is our x's. But we have points of discontinuity, points that are breaking up the continuous nature of this graph. So we go from negative infinity to -2. We're going to hop right on over -2 and go to 3, and then hop on over 3. And then I didn't mean to leave such a big gap, but 3 to infinity. Remember these parentheses instead of brackets. Parentheses mean we're not including these values, but we're going up to it. So it helps us show that we're skipping over those two numbers. Okay, wholes are any factors that get canceled out in the denominator. So we have a whole at x equals 3. We have a vertical asymptote at x equals -2. And now our m, which is the numerator, m of 3, n of 2, m's bigger, which means the numerator will get bigger and bigger and bigger faster as we plug in bigger numbers, faster than the than the denominator. So we're just, there's no horizontal asymptote. And you can look back at that and have a look. All right, try the homework, 7.1, day 2. See how you do. There's actually no quiz for today because it's just kind of a repeat of last class. But I will, before we begin the next lesson, I'll just do a quick review. All right, let me know if you need any help. Have a great day.